session of the VSET for this term. So today we're very happy to have Qingmin Liu, who's going to talk to us about a cooperative analysis of incomplete information. And we're very happy to have our two panelists, Doran Ravid and Roberto Serrano. Just to remind you the format of these seminars, which is as follows. So we have a 60-minute presentation with time for interim questions from the panelists, but also from the participants. You can also post your. Actually, we don't have the comments for the text, but so I guess it's better if you just do it orally. Just to remind you that the talk is recorded. And so before I hand over to Qingmin, let me announce the next talk. Next week is going to be by Alessandro Bonatti, who's going to talk about the economics of large language models, token allocation, fine-tuning, and optimal pricing. And the panelists are Ron Siegel and Frank Yak. So Qingmin, the floor is yours.
Okay, so thank you very much for the invitation. Today, my talk is a cooperative analysis of incomplete information. I am with Columbia University. So before I gave the talk, I would like to say that when I gave the presentation, I will not be able to see who write in the Zoom. If you have any questions, feel free just to stop my presentation and speak out. Thank you. Hey. Okay, so here's the motivation of this project. So I would like to consider cooperative games with incomplete information. What I want to emphasize is that we have a lot of work on non-cooperative games with incomplete information. At the same time, we also have a lot of papers on cooperative games with complete information. But somewhat surprisingly, we don't have a lot of work on cooperative games with incomplete information. Okay, and why want to study cooperative games? I think this is more or less a common knowledge that cooperative models have its own advantage over non-cooperative models. For example, if you want to model a complex interaction like matching a marriage problem, you have to write down how people meet each other and who is going to make the proposal, and when the two players decide to marry with each other, and what do they do? Okay, do they leave the market? Do they stay in the market and continue search? And so on and so forth. So if you want to model those details in a non-cooperative game, the model will become very complex. And of course, if we do not understand the empirical contents of the game we study, our model become unreliable. So cooperative game has the advantage that it's a reduced form model. It's not going to make a lot of assumptions. So basically, we make predictions based on the payoff assumptions alone. That's usually the case. But of course, I'm not saying that cooperative games is superior, because cooperative games usually do not make precise predictions. If we do know how the interaction is conducted, for example, we do know in some platforms what is the rules of the game. In those contexts, perhaps non-cooperative games are better models. But if we do not know the details, cooperative games are simpler models and reduced form models. And I'm not the first one to make those claims. Fisher, 1991, in one of his book chapters on organizing industry organization, he was already making the claim that, the non-cooperative game theory perhaps too smart. We can come up with a lot of non-cooperative models, rationalize a lot of predictions. So the question is, which model we're going to believe. Okay, so this all says that cooperative game has some advantage. We can make predictions without making too much assumptions, even though the predictions are too weak sometimes, but they're simple. Okay, the literature of cooperative games with incomplete information really started with the paper by Bob Wilson, 1978. And his paper generalized the core concept in an exchange economy with incomplete information. And there are a lot of developments since Wilson's seminal paper. And Allman Hafiz in 2002 conclude in their book chapter on incomplete information games with the following sentence. They say that, oh, this area is to this day fraught with unresolved conceptual difficulties. And they're making reference to cooperative games with incomplete information. There are many open questions, and many of them are conceptually difficult. There is an excellent survey paper by Forges and Serrano. They list a number of very difficult conceptual questions that has yet to be resolved. Okay, so we have many very good theories, mostly in abstract framework, but we don't have a lot of papers on cooperative models with concrete applications. So I think when a theory literature run into some conceptual troubles, it will be better to look at concrete application, try to see whether the structures of those applications give us some idea about how to proceed. Okay, so before I introduce the kind of applications that I want to study, let me summarize my understanding of the difficulties of the literature. Okay, I think the first order difficulty with cooperative games with incomplete information is to model players' inferences without a well-defined non-cooperative games. If we have a non-cooperative games, we define the game form, who is going to move first and who is going to move second, what player observe before they move, and what's their strategy space, and so on and so forth. When we define those details very carefully, the analysis of the incomplete information games become very simple, at least conceptually. Okay? Starting from Holmstrom, Myerson, 1983, that's another beautiful paper. They introduce a concept called durability. Their idea is to reintroduce some non-cooperative elements into this otherwise cooperative framework and define a coherent solution concept. So that's their idea, and a lot of papers that follow this line of research, which basically introduce some non-cooperative elements in a cooperative framework. But again, as I mentioned earlier, that I would like to have a cooperative framework without making too much assumptions on the nature of non-cooperative interactions between players. So there are, of course, other complicated issues. Forges and Roberto's survey mentioned some of them. Okay? So when we talk about deviation, collisional deviation without a well-defined game form, we want to ask, whether deviation take at ex-ante stage or interim stage, or are we talking about interim deviations from ex-ante plans? Okay? And there are also information on strategic externalities, right? So a deviation of a group of players has some externality on players not in the deviation group, and players outside of the group can do something that affect the payoff of players in the deviation group. And of course, there is also an informational aspect of it if you introduce incomplete information into the problem. Those are all kinds of difficulties. Okay, but in this paper, I'm going to introduce a simple idea. Okay, and I would mention that this idea is motivated by the particular kind of applications that I want to look at it. So what is the departure from my approach? What's the departure of my approach from this literature? So first, I would like to say that no matter how you model the process of belief updating or the inference, the Bayesian players eventually will reach some beliefs. Okay? They will reach some beliefs. So my approach is to specify those beliefs without modeling the process that lead to those beliefs. After those beliefs are in place, then I can talk about whether there are simple tests that those beliefs, together with some outcomes, will give us a reasonable solution concept. And only after that, I will make restrictions on those beliefs. And I'm going to say, oh, those beliefs are reasonable, those beliefs are not reasonable. By making those restrictions, I end up refining the solution concept. And then we'll make predictions based on those refined solution concept. So that's basically the idea. Okay? Nothing very complicated.
So
Yes,
Qingmin, your first slide start with some fighting words against non-cooperative game theory. I waited as long as I could, I think, before I did a little bit of a response, and I think this is maybe a good place.
Please.
So you're right. In non-cooperative game theory, we make assumptions on the process in which we're going to do things. And in non-cooperative game theory, it seems that when we define the environment, we make very few assumptions. I think the approach you're highlighting and the conceptual issues that were brought up kind of point out that in non-cooperative game theory, we're still making a lot of assumptions. It's just that they all go into the solution concept, right? When you're assuming what deviations we're considering, what beliefs are going to be reasonable. So, I'm not sure that necessarily I would have agreed with the statement that this is going to be an environment with less assumptions than what we're used to. It's just the assumptions are placed in a different, in a different container.
I agree with you. Okay, so let's look at a particular example. For example, marriage matching problem. Okay? I think there is a reason that the pairwise stability as a solution concept become very popular for this type of problem instead of a non-cooperative game model of marriage matching, right? Of course, a lot of things has been assumed, has been encoded in pairwise stability, the solution concept. And till this day, we still do not fully understand those assumptions, right? But stability feels like a reasonable concept. It feels like an intuitive criterion for us to analyze those market, right? But if you want to write down a dynamic game model of marriage model, it will become quite complicated, even though technically you can still solve it. With incomplete information, the non-cooperative games certainly will become more complicated. But the question, of course, is there a counterpart of pairwise stability in the environment of incomplete information? I'm not going to say that my solution concept is going to be assumption-free. I am going to make a lot of assumptions to define stability with incomplete information for the marriage matching problem. And a lot of those assumptions will make people uncomfortable, but at least I think that those concepts is going to be simpler than what we see in the non-cooperative models. Okay, but we can talk about that later when I introduce the solution concept. Certainly, I'm going to make a lot of restrictions. A lot of them are debatable.
Okay.
Okay. Okay, so now let me talk about the applications I have in mind. Okay, marriage problem, network problem, and labor market, for example. So there are several features of those markets. There's no planning stage. Okay, and also recontracting opportunities arise after players see what they get. Okay? In the marriage problem, players want to deviate after they see who is their partner. Okay, they do not deviate at some planning stage. Okay. The other thing I want to mention is the information associated with the solution concept now is a fixed point. What do I mean by this? Okay? If we look at the incomplete information network formation problem, after we see the kind of network we are in, okay, and this observation reveals information, right? So the network being stable says something about the information player has. Okay? If they have different kinds of information, perhaps this network is not stable. So therefore, to define the stability of the network, we have to define the information associated with this particular network. Roberto, do you have a question?
No.
Okay. Okay, so now let me introduce the formal model. Okay, I have a finite set of players denoted as n, and each player n's type is theta n coming from a bigger type space. The state space is just the product of their type size. And each player n is going to have a prior belief. I do not have to assume common prior at this stage. And I'm going to denote the set of feasible outcomes as z, okay, the big size z. Each player's payoff depends on the entire type profile of all the players and also the outcome. Okay. In collision games, we're going to have a collisions. Okay, a collision is basically a subset of those n players. Okay, I'm going to specialize to particular application later on, but at this point is quite general. Okay, from each outcome Z, okay, what this collision S can do is to collectively deviate to Z prime. Okay, so I'm going to write the restriction on this collision as D. Okay, D is basically said that okay, for each collision S and for each prevailing outcome Z, okay, they can go to a set of outcomes D of S comma Z. Okay, the restriction I have is that D does not depend on theta. Okay, the realization of the type profile does not affect the feasible deviations. If I do not have this assumption, things will become more complicated. I can still provide a solution, but it's going to be more complicated. Okay, now a game of incomplete information is summarized by those elements. Okay, the collation, the most important thing is the set of collations and the feasible deviations of a collation. Okay, so what are the special cases? Network formation. So in a network formation problem, the feasible outcome Z is going to be just networks, okay, all possible networks. And matching, for example, the feasible outcome just who is matched with whom. And if you want to have transfers, this feasible outcomes also should describe what is the transfer paid to each other. Exchange economy, okay, Z is basically the allocation. And if you want to study exchange economy with prices like competitive equilibrium concept, this outcome Z also includes a price vector. Okay? So at this point, it's pretty general for the purpose of describing the solution concept. It's okay, but if you want to prove some results, I better make some assumptions on the structure of the game. Okay, so for complete information game, okay, we mean that what theta is common knowledge. Okay, this type of game is well understood. Okay, and the solution concept is as follows: an outcome Z is a stable outcome of a complete information game when theta is commonly known if there do not exist a collation S and an alternative outcome Z prime that the collation can deviate to, okay, such that every player N in this collation will benefit from the deviation, will strictly benefit from the deviation. So that's the concept for the complete information game. Okay? And this concept is quite well understood, right? So let's look at the special cases. In an exchange economy, this concept is basically the core concept. Okay? And if you want to introduce a price as part of the outcome, you can also describe Voronezh equilibrium into this concept. There, the deviation is just unilateral, right? You do not consider all possible deviations, you only consider unilateral deviations. You can also consider stable networks in this framework. There, the deviation is just either unilateral or pairwise. Okay? You can also consider stable matching. There, one-to-one matching problem, this Z describe who is matching with whom, okay? And the deviation is either unilateral or pairwise. Okay? So this concept, the core concept, is actually pretty nice and pretty simple because it does not say how this collision S comes together and how this collision come up with the alternative outcome Z prime, and also didn't say how Z, the stable outcome, arise in the first place. Okay, and I think that's yes, please.
Roberto here. Isn't giving the Voronezh equilibrium as an example here a little misleading in the sense that, I mean, there you're already imposing restrictions on which coalitions can form, namely individuals, as opposed to, I mean, I guess when you talk about matching, you talk also about just pairwise stability or something, but I mean, just as it stands, the definition you wrote, in principle, allows for any S, right? Any coalition to
yes. So this calligraphic,
yeah.
Yes. So thanks for this clarifying question. This calligraphic S is a primitive of the game, right? So I do not allow, I do not necessarily allow S, the calligraphic S, to be all subsets of the Cyto players.
Okay.
Yeah. So in the Voronezh equilibrium formulation, I would just say that S is the Cyto individuals, right? And that would describe Voronezh equilibrium I don't think that's very difficult to see if,
Yeah.
yeah. But the only said that
Okay.
this concept
So I
it
didn't.
is well understood, in different contexts. Yes,
Yeah. I mean,
please.
so, some things that some people argue that if this thing is like, for example, too restrictive in the sense that it considers all deviations, right? Even ones that are themselves later would be broken if we were to try to form them. Right? So it's not that this concept is without assumptions, right? It's, for example, restricting us to like thinking about all possible deviations in your set S. And it doesn't allow, even though there are some deviations that given this particular, proposal would not be accounted for. So like, all these like literature on farsightedness and so on criticizes this way of thinking.
Absolutely right. Yeah. So, here, this solution concept only tests whether an outcome Z is immune to a particular deviation in this site D, right? So if you want to, for example, you can also formulate a pure straight Nash equilibrium in this setup, right? So we do not consider the far-sighted deviation of Nash equilibrium, for example, right? Only test whether outcome is immune to one step deviation. We do not talk about deviations after deviations.
But that is only one player, right? Here, the whole point was like that you're thinking about coalitions usually when you're thinking about the cooperative games. Thinking about
Yes.
we're trying to go together. The pairwise stability, right? We say, oh, I'll deviate with you and form a new pair. But at that point, there's this question of like, but then would the other person want to switch away from me? In the Nash equilibrium, it's just me, and if I prefer to switch, then I benefit from it. Then if it's a repeated game or so on, then I might suffer consequences later, but it's all part of the equilibrium. Here, we're moving as a pair, and I need to trust that, or as a set, and I need to trust that everybody is going to stay in the deviation once we've done it.
But that was his answer to my question, as I understood it. I think script S is a primitive of the model describing the set of coalitions that can actually be active in this problem. If that set is just the set of singleton coalitions, then yeah, you can talk about a concept that relates to either Walrasian equilibrium if you allow prices, or Nash equilibrium, or whatever.
Right.
If you talk about pairs, you're going to talk about pairwise stability. If you talk about any coalitions, you're going to talk about the core. And I think Qingmin's answer was exactly right. Understanding that this script test is just one of the important primitives.
So
yeah.
So my understanding
is it was raising a different issue with the stability. Which is that it does make assumptions that that some people have criticized that you can't, and I don't think you can incorporate like farsightedness into this S or into the D, right?
I'm not going to incorporate this farsightedness in D, right? So if you want to consider farsightedness, you want to consider, okay, this D is only the feasible deviations, not necessarily the deviation that you would like to go, right? So if you want to incorporate farsightedness, you're not going to change D, which is the primitive of the model, but you're going to incorporate further deviations. So people will consider whether it's optimal to deviate to Z prime, anticipating that if they deviate to Z prime, there could be a further deviation to Z double prime. They have to think about that, right? But that's not going to be restriction on D. My understanding about the Ron's question is that, it seems reasonable to consider far-side deviations in the collisional setting, but perhaps it's less natural to consider the far-side deviations in Nash equilibrium, unilateral deviations, right? But I would say that, mathematically this looks very similar, right? So, pairwise deviation. If I deviate with you, tomorrow you might deviate with Roberto. But when I think about this, I would say, hey, I could imagine a similar situation in Nash equilibrium setup. If I deviate today from deviation to cooperation, I might think about you after I deviate to cooperation. you want to deviate to something else tomorrow, right? That does not involve me, right? So I think that if you want to consider far-sightedness in the collisional setting, it's also natural to consider far-sightedness in the unilateral setting. But you're absolutely right that most of the discussions about far-sightedness happens in the collisional setting, and there are lots of examples where far-sightedness make sense in the collisional setting. But here, I'm not going to touch that, right? I am just going to extend the solution concept like stable matching, stable network, and core of exchange economy, right? I'm going to extend those well-understood concepts into the incomplete information environments. I'm not going to extend this concept into the far-sightedness. But of course, if you want to incorporate far-sightedness in the incomplete information environment, that will be a new project, which I do not have much idea about it, but we can talk about that later. So,
I will not take more. I will say, I think there was a response in the non-cooperative world that's not quite available in the cooperative metaphor. But we should go on. It's not worth wasting our time here.
Good. Yeah. Okay. So, so when I say those, the solution concept is agnostic about those elements. But if you think about the classic concept of Nash equilibrium, okay, we didn't ask, okay, how a deviating player come up with a particular deviation, okay, and we do not ask how the Nash equilibrium arise. At least in the definition of Nash equilibrium, those elements will abstract away. Okay, but of course we are interested in how a Nash equilibrium arise in the first place. And similarly here, we're interested in how a collisional stable outcomes arise in the first place. But I'm not going to answer those questions in this paper. Okay, so let's describe the formulation of the solution concept. Okay, a playout of this game, pi is going to be a function from the state space to the outcomes. Okay, so here basically, if I want to describe a theory that predicts how the game is played, there will be a mapping, right? That tell us, if the true state is theta, some particular outcome z is going to be realized. Okay, I could incorporate lotteries over outcomes, but I will prefer not to do it. And you will see that you can extend this basic formulation to that setup. Okay, now what is collisional deviation associated with the playout of the game? Okay, a collisional deviation involves the side of players S, an outcome z from which they deviate, and z prime, and the outcome they deviate to. Okay, and the restriction is that z prime has to be feasible deviation. Okay, and z, okay, the starting point, has to be the prediction of the playout. Okay, you deviate from something that is an quote unquote stable outcome or equilibrium outcome, right? So we are basically testing whether a playout or the outcome associated with the playout is immune to deviations. Okay, so what is the scenario of deviations? A deviation happens at some state theta, okay, when z is the realized outcome. I will call this the scenario of deviations, and sigma subscript pi is a set of scenarios of deviations. And of course, player n does not necessarily knows other players' types. So therefore, player n's perceived scenario of deviation is just a deviation and his own type, theta n. Okay, I'm going to denote sigma pi comma n, the player n's perceived scenarios of deviations. Okay, so I'm going to describe a belief system associated with this playout of the game pi. Okay, so this belief system is going to describe beliefs for each player associated with each scenario of deviation perceived by this player. Okay, so player n's belief mapping is going to be a function from what he perceived, okay, at that deviation to a probability distribution over all players' types. Okay, so for example, if a perceived deviation sigma, okay, sigma n, okay, is given, then the player n is going to have a belief associated with sigma n. Okay, there are two natural restrictions. One is that player N must know his own types, right? This is a very natural restriction. Okay? The other restriction is that his belief has to be consistent with the theory we try to develop, right? So if we know, if the player know that the outcome Z, okay, is realized from this playout pi, okay, they will figure out, oh, what is the set of states that give out this Z, okay? And as this deviation scenario perceived by player N will assign property 1 to this set of states. Okay, that's what I call the knowledge of playout. Okay, and the assessment of the game consists of the playout of the game pi and the belief system associated with this playout. Okay, those terminology come from Krebs Wilson. Naturally, I will make a comment later on. Okay,
Qingmin,
so,
I have just a
yes.
clarification question. Sorry.
Mhm.
So is there anything somewhere in this belief system that tells me kind of what is people's beliefs when they are like when at the state where they got matched, but they didn't yet try to do any deviation from the match? Is it encoded
Well,
somewhere in?
Yes, so you will see that later. Okay, so I would delay that. Okay, but at this point, okay, as I said, I am going to study the beliefs associated with each possible deviation, right? But what you are saying is, oh, what if that there's no deviation? What is the belief associated with that, right?
Yeah.
Okay, yes. So I can give you the answer now. I just read Z prime to be Z if C prime is a feasible deviation. That means that they do not want to deviate. Okay.
Perfect. So that's
Okay.
what I was wondering if it's
Yeah.
encoded somewhere. Okay, good. So that's where
Yeah.
it is. Okay.
Right. But I would like to derive that as a result of the restriction of the belief instead of impose it. But you can do that if you want to. Yes. Okay. So when the belief system is in place, okay, so each player has a belief associated with each perceived deviation. Then we can talk about whether the player want to have that deviation or not, right? So, and that is trivial to define. Okay? A scenario of a deviation is viable with respect to the belief system if all players involved in this collision will benefit from the particular deviation given their beliefs. Okay? That's what I call a viable scenario of deviation. Okay? They know where they deviate to, and they know what's their belief associated with this deviation. Now they can just compute their expected payoff from this deviation. So this is very simple, right? The definition, the basic concept. An assessment is stable if there is no scenario of deviation, okay, is viable with respect to the belief system. Okay, so that's basically the definition of stability for the incomplete information environments. All it takes is to specify each player's belief associated with each deviation, and then we can talk about their expected payoff for deviation. And assessment is stable if their expected payoff is such that there is no profitable deviation. Okay. Okay.
Sorry, can I
So
have a
yes.
very short clarifying question? So that I understand, when there is players or coalition members consider this viable outcome, that process does not generate any updating about the belief, or is that hidden somewhere and part of the process? That's the bit I'm missing.
Very good. So I'm going to get there, but at this point, I'm basically specifying for each deviation scenario, whatever the process that lead to this belief. I'm going to just ignore that. I'm going to write it down, write the belief down here. Okay, there could be a process, and that process involves what I learned from observing other players' deviations, and that will lead to the same belief beta n here, right? So no matter what is the inference I'm going to make, I'm going to reach some belief beta n here, right? I'm going to write it down. So at this point, okay, I'm going to be silent about what you say. But of course, what you say is going to lead to some restrictions on the beta n, right? I'm going to do that later. So that's precisely what I'm going to do. Okay, so I will call this a Krebs-Wilson program for cooperative games. Okay, so what Krebs-Wilson did is that, let's look at a extensive-form game. Okay, we're going to specify a belief, okay, at each contingency, and we want to ask whether players, okay, have a deviation given their belief at those with those beliefs at each of those contingencies, right? So here, I didn't do something dramatically different. I would just say, there are contingencies of deviations, and let's specify the player's belief at those contingencies, and then we evaluate their deviation. Okay, we are in an equilibrium situation, in a stable situation, if the belief is such that players do not want to deviate. Okay, so that's why I call this Krebs-Wilson program for cooperative games. Okay, but of course we do not have game trees and strategies, so it's unclear how to make further restrictions. Right, Krebs-Wilson, their paper inspired a lot of further refinements of their solution concept, a lot of belief-based refinements. So you can talk about those belief restrictions when you have a game tree, but here we do not have it, right? But we can still do something as Max suggested. Okay, there should be something we can do. Okay.
But
so
if I understood correctly, Qingmin, so you're calling a deviation sigma, right? That's a
yes.
So in principle, there could be many ways in which or through which a coalition arrives at that deviation sigma, right? I mean, I'm thinking of the coalition ends up coming up with this deviation sigma after a very simple conversation that takes basically 1 minute, or it reaches sigma after this more complicated process that eventually they figure out what to do, what not to do, and they end up with this same sigma. So
Yes.
implicitly here you're saying sigma is what matters, not really the process through which these people arrived at this sigma, and therefore these different protocols of how to arrive to sigma in principle could be associated with very different beliefs. So you're basically saying none of that will matter for me. I just want to pay attention somehow to this sigma. And for this sigma, there is a unique belief that is generated with that, associated with that sigma, right?
Well, so yes. So let's say there are two ways to lead to this sigma, right? So sigma itself, right, didn't say what is the precise behind it, right? Let's say that you have two players. Suppose one player has private information, the other player does not have private information, and they come together. They want to deviate. Okay, one way to think about the non-cooperative process behind this deviation is that the informed players make a proposal about where to deviate, and they end up saying, "Oh, let's deviate to Z," right? The other process is that the uninformed players and make a proposal, say, "Oh, let's deviate to Z," right? And even though they all end up with this particular deviation sigma, but one is proposed by the informed player, the other is proposed by the uninformed players. We know from non-cooperative games, this two process would generally give us a different kind of inference, right? So that's why we have a signaling and screening problems, which define different kinds of games. But what I'm saying here is that I'm not going to uniquely pin down the belief associated with this deviation. Okay, I could have, in one solution concept, right, in one equilibrium, there will be one belief associated with this particular deviation. There could be a second equilibrium that have a different belief, but also associated with the same kind of deviation, right? I'm not saying that I'm going to uniquely pin down the belief. I'm just saying that, a different process will correspond to two different beliefs. If both can be supported as stable outcomes, then both are quote unquote equilibrium, right?
I see.
And I think this analog with the equilibrium is clear, right? So it's yeah,
I understand. Thank you.
Good. Yeah. But of course, they said that, because there are all kinds of processes that lead to beta, the belief, and there are all kinds of belief beta that will pass this test of stability. And the question is how small the site of stable prediction is, right? That's going to be the question I have to address. Okay, so after I created this basic idea to Krebs-Wilson, I want to ask the following question. How do we refine this solution concept? Okay? I'm going to bring in another literature that most people are familiar with. It's the models of no-tree theorems. So when the no-tree theorems, we're basically asking the following question. Okay? Under what conditions that we have absence of trade? Okay? And usually we define trade as mutually agreeable transactions, okay? Without making reference to the institutional details or how players come up with the trade, who proposed the trade, and what is the institutional details that determines the formation of the trade. But the no-trade theorems in several papers that we're all familiar with is basically defining the conditions under which there is no mutually agreeable transactions. Okay, but here I will interpret stability as defining a no-trade situation. Okay, so you are already reached in a situation, and you cannot find a group of players that find an alternative trade so that they both want to move there. Okay, so instead of giving conditions under which we don't have further trade, I want to ask, given that we are in a situation with no trade, what's that situation? Okay, what is the property of that situation? That's what I interpret. That's how I interpret this stability. But of course, the definition of trade is in abstract form, right? That's very much like what I do here. And if we look at this no trade theorem literature, there's always some additional structures, like a common knowledge of mutually agreeable transactions, right? So when I evaluate whether I want to have a trade with you, okay, I have to take into account that you are also evaluating whether you want to take you want to have the trade with me. So a trade is viable. It has to be that it's viable, conditional on that we both believe that is viable. So in the sense that there's a common knowledge of mutually agreeable trade. So that is a restriction, right? That common knowledge is a restriction. So we're going to bring in the same kind of restrictions to the definition of stability. Hopefully that will give us some restrictions on the beliefs. Okay, I think that's consistent with what Max just said. Okay, so now
Can I have a
yes, please.
So one instance of like the cooperative modeling, as you mentioned before, is stability, right? And in stability, some people, you have some work about stability with imperfect information. How does this definition relate to like the definitions that are out there? It seems, from my memory, it's very similar, but you were the one who wrote. So, right. So when we've had stability, like, as we know that if you have like a stable matching situation, the core is basically just stable matchings. It is, but like the definitions, there's some subtlety in the definitions here. Is this way of defining, if I restricted like the definition you have here to situations where all we can do is like pairwise, are we getting back like the definitions that you have in your, in the stable matching with imperfect information or the papers, or is this different?
I will get back to that question perhaps in 5 minutes. Okay.
Okay.
Yeah, I am going to consider the matching applications. Okay, so what is the difference between this approach with existing literature? I think the existing literature is trying to accomplish a bigger task, a more complex task. So I think the literature is trying to model the process that determines how the collation is formed and how the collation aggregate their information, and in this will in the process will determine how the belief is formed. Okay, and sometimes those literature also consider the implementations of the solution concepts. So this is a very, very complicated object, right? And as you can see from what I described so far, I'm not doing those things. I'm just saying that no matter what is the process, there will be a belief associated with the deviation that they arrive at. And then we're going to just define those beliefs explicitly. And the belief is going to give us a test which determines the solution concept. And then we're going to impose restrictions on those beliefs. Okay, so the many beautiful theories, but they don't have a lot of concrete applications. But I'm going to consider some applications to show that this concept could have some restrictions with some refinements. Okay, so I have to go a bit faster. So let's look at a particular class of games which has private value. If we do not consider those coefficients A and B, it's just that each player's payoff only depends on his own type. Okay? In this case, the notion of stability I just introduced does not give us anything more than the complete information stability. So basically, if we have a game that has a private value or slightly generalization of that, then the incomplete information stability is just state-by-state complete information stability. Okay, so therefore we want to consider some interdependency of players' types. Okay, and each player's payoff would depend on not only his own type but also on other players' type. Okay, and to do that we need to make further restrictions. Okay, what is the basic idea? Okay, so the basic idea is that for collation to form, it should be common knowledge among the players in that collation that everybody benefit from the deviation. Okay, if I state it in terms of the no-trade theorem models, that it's basically for a group player to trade, it should be common knowledge that everybody benefit from this particular trade. Okay, so I'm going to formulate this idea. That this idea is going to restrict the belief system. Okay, so give us given a assessment pi beta, a player M in this collation benefit from the deviation, okay, according to his belief system beta, okay, if his type is such that he finds Z prime, okay, give him a higher expected utility than outcome Z, okay, and we look at all those types of player M, okay, we call this player M's deviating types. Okay, so now let's look at all players' deviation types except for player N. Okay, when player N look at his this particular deviation, okay, he should assign property 1 to all other players are benefiting from the deviation, right? So therefore, he should assign property 1 to this particular site. Okay? That's the restriction we want to impose in the first place. We say an assessment is basically consistent, okay, if for all perceived scenario deviation of player N, okay, if he thinks other players possibly benefit from the deviation, then his belief is going to assign property 1 to that set. Okay. Here I'm not defining the belief beta N. This is basically an additional restriction on beta N when beta is already, the belief system is already in place. Okay. So that is basic consistency. So basic consistency is the minimal restriction that is consistent with common knowledge of mutual gains from a collisional deviation. Okay? And if you are interested in epistemic game theory, you can actually write it out more explicitly, the gains and common knowledge of gains and so on and so forth. Okay. I think I have an issue that, okay. Okay, so, but that basic consistency sometimes is not strong enough. I am going to introduce a stronger version of it. I say that an assessment is weakly consistent, okay, if for every perceived scenario of deviation for player N, okay, player N's belief is updated from his own prior belief contingent on the following things. The first is that his own type. He knows his own type. The second is that he knows that outcome Z arise from this play out pi. Okay? He knows this is the set of possible type possible states that can give him the outcome Z. And then he also knows that other players benefit from this deviation. Okay? So weak consistency is a strengthening of a basic consistency. It said that not only a player assign property 1 to other players benefit from the deviation, and that's the only thing. And I'm going to assume that that's the only thing he inferred. Okay? So there's a lot of assumptions behind this, right? There will be you could imagine different process of information exchanges between the two players in a deviation. But here, this condition said, okay, this condition said we do not care about that. We only care about the set of types of the other player that benefit from the deviation. There are lots of signaling and screening going on, but we don't care. We just look at, what is the set of type that make the other player benefit from deviation? And we're going to update the belief, the prior belief, by conditioning on that. So that's what I call the weak consistency. Okay, so I think I seriously run out of time, but let me go through several examples. So here I have an example of two players. Each player has 2 times, and there are 2 outcomes. One outcome Z is an outside option, and the players' payoff, regardless of their type from the outside option, is 0. And their payoff from outcome Z prime depend on their types. Okay, so that's the payoff from outcome Z prime. Okay, let's assume that there's a uniform prior on the state space. Okay, I'm going to claim that the playout pi that specifies the outside option, regardless of the state, is stable. Okay, it's stable according to the very first definition, but it cannot be basically or weakly consistent. Okay, so why this can be stable? All we need to do is to come up with some belief system that support no deviation, right? So the outcome is Z. They get payoff 0. Okay? Let's look at player 1 whose type is theta 1, 1. Okay? He benefits from the deviation. He benefits from the deviation, but it depends on whether the player 2 wants to join the deviation or not. If player 2 believes that player 1 is actually the second type, player 2 does not want to join the deviation. Okay? But if player 2 does not want to join the deviation, okay? If player 2 does not want to join the deviation, and this collision is not formed, but we still have to say, hey, whether player 2 can have this particular belief. Well, given that there's no restriction on the player's belief, and the only thing we have is test the consistency of belief, this and the playout pi, this can indeed be stable, and you can complete the argument yourself, but this cannot be basically consistent. Why that's the case? The basic consistency is that in each deviation scenario, you have to assign property 1 to other players benefit from the deviation. Let's look at player 2. Now they can no longer assign property 1 to the other players, to player 1 being the second type, because the second type does not benefit from the deviation, and the first type benefit from the deviation, right? So therefore, player 2's belief under basic consistency will say that they will assign property 1 to the first type. And if player 2's type is theta 2, 1, he assigns property 1 to the first type, player 2 will want to deviate. Now player 1 will always want to deviate when his type is the first type, so there is a deviation when the type is theta 1, 1, theta 2, 1, right? So therefore, this cannot be basically consistent and cannot be weakly consistent. Okay, so now let's look at the second example with weak consistency. Okay, again, we're going to have 2 players and 2 types and 2 outcomes, and outcome Z is outside option. All players payoff is 0 regardless of their type, and their payoff from Z prime depend on their type. Okay, so if we look at this particular game, okay, on top of that, we're going to introduce transfers. We want to ask, can the outcome Z, okay, the no trade outcome, be consistent with stability. In particular, whether it can be consistent with weak, consistent, stable. Okay, weakly consistent belief and stability. The answer is yes. We just have to construct the belief system. Okay? I don't have time. I have to really rush. But the basic idea is that their belief has to have this fixed point property. Okay? You assign some property to the other guy has this particular type, and you also have to justify the other player's belief for that particular type, and so on and so forth. So there is a fixed point property. So let me skip this example. Okay, and this example is something I have to really cover. Okay, again, 2 players, 2 types, and 2 outcomes. Outside option give player a payout of 0, and this Z prime give a player this payoff. Okay, so my claim is that this game without transfers can actually without transfers can support the following playout as a stable assessment. Okay, basically their belief system is uniform. Okay, regardless of their type, they assign equal property to the other players, type being type 1 or type 2. Okay, this can be weakly consistent. I'm going to skip the argument there. But if we look at this outside option Z, okay, and at this particular type realization theta 1 1 theta 2 1, okay, it feels like the 2 players can actually deviate, right? So what is the kind of deviation we can imagine? Well, player 1, when his type is theta 1 1, he said, look, okay, my type is theta 1 1, and I want to assure you that I have no incentive to lie, and I want to deviate to you with you if your type is theta 2 1. Player 2 can basically say the same thing if his type is theta 2 1, right? Here clearly no incentive, there's no incentive for them to lie, okay? And these 2 claims have the property what I call the mutually reassuring, okay? So if we think these mutually reassuring claims are plausible, then we can refine the weak consistency concept even further, okay? As I said, that is no trade outcome is actually stable under some weak consistent belief, but it's going to be refined away by this kind of reasoning. Okay, so this is not the first time this idea arise. So in the trading problem, the no trade theorem problem, John Levin 2003, he come up with a similar example, and I want to mention that is one of his homework problem for his second year PhD class, and the similar idea also appears in Data and Walras' credible core concept, and the credible core concept is actually based on this idea. Okay, but there's a big and subtle difference from those ideas from what I'm going to formulate. First, this Z prime, where you deviate to, okay, is not state contingent. This is a typo. It's a state contingent. So if you do not allow state contingent deviations, okay, you actually make fewer deviation possibilities available. Okay, so this means that you tend to restrict the concept. Okay, the other thing is that the Z, okay, the prevailing outcomes, also reveals information which is not in those papers. They also make some restrictions, okay, on the feasible deviations. And of course, there is also a zero probability one. That's something that that I have to take care of. So actually, those 3 things make things a bit complicated. And here is the notion of mutually reassuring deviation. So I'm going to say that for each player in the collation, I'm going to specify a site Dn. Okay, and this collection of sites are mutually reassuring, okay, if the following condition hold. Forgot about the first. Okay, let's look at the second one directly. It basically says that the player n's set, okay, consists of all player n's types, such that, okay, he will find the deviation profitable, okay, given his belief. And what is his belief? His belief is updated from the prior belief conditional on other players' type is in their respective DNs. So basically, find a bunch of types such that conditional on the other player's type is in their set. Okay? The set of types at which I want to deviate is exactly my DN. Okay? That's this fixed form property. I'm going to refine weak consistency by imposing this restriction. Okay? An assessment is strongly consistent if not only it is weakly consistent, but also if but also a deviation is viable if you can find such mutually reassuring size of deviations. Okay, so that's the refinement. I'm going to impose this condition. Okay, and here is okay. I run out of time, but let me use 2 minutes. So here is the relationship between weak and strong consistency. If assessment is weakly consistent, then a deviation is viable only if there are mutually reassuring signs for the deviation. But the strong consistency imposes if and only if property regarding mutually reassuring signs. Okay? But weak and strong is going to be the same in the case of one-sided incomplete information. Okay? So now let me come back to Daron's question about the matching. So previously, my paper with matching with one-sided incomplete information will correspond to a weak consistency. And in that particular setup, there is no distinction between weak consistency and strong consistency. When you have two-sided incomplete information, or more complicated setting, you need this strong consistency, okay, to make further predictions. And weak consistency is not going to give you a lot of predictions. Okay, so here there is an existence property. As you see from that two-player game with transfers, that in order to construct weak consistent beliefs, you have to make sure that those beliefs have this fixed form property for each continuously. So the proof is a bit messy, but the proof is constructive. Okay, so I have this matching applications. I'm going to skip this. Okay, I do want to mention that there's a few papers on matching with incomplete information, and the paper that Doron mentioned is this paper, the one-sided incomplete information. Okay, so if you are interested in this application, you can look at the paper, but the basic result says that strong consistency can indeed have some restrictions on the two-sided incomplete information matching problems, and that's the theorem. It basically said that you can get some kind of efficiency result. Okay, incomplete information efficiency and stability are basically the dual concepts. But here with incomplete information, they are not. Some additional restriction had to be imposed. Okay, so I'm going to skip this. And network is another application that fits the general framework. You can talk about stable networks. And you can impose some conditions and show that a strong consistency will imply sometimes that incomplete information stable network has to be state by state complete information stable. Okay, so this is my conclusion. That's exactly the introduction slide. Okay, let me stop here.
Okay, thank you very much, Qingmin. It was very interesting. So I will first ask our panelists to make some comments and then to open the floor to other participants if they want to make any questions or comments. So first, Doron, do you want to?
First, I need to apologize because I asked some things that were probably better left for the comments at the end, in the middle of your talk. And so I should have waited with that. I mean, I think that, this is a very interesting approach, and I think it's like nice that, you're sort of putting the very minimal, place of saying there's going to be some beliefs that we're going to get to if we deviate, and let's just think about that. And I think that's like very nice. I guess one And I already commented about the fact that I think there is, you are putting, there is some assumptions are being made. They're just being made in like that stage of the solution concept. That my comment of far-side stability was related to that in the sense that it's just like people have criticized stability as being too restrictive in various ways, and sort of because it's assuming, a particular process in some sense, and you're the going back to that, I think, and you were responding to my notion of a far-side stability with, well, you should be also maybe imposing this Nash equilibrium. That I'm not sure. It's because when we're writing our incomplete information, the non-cooperative game, we're usually thinking of that's the world. There's the question of how do we get there and so on. We're kind of thinking that's the world. That's it. When we wrote a one-shot game, it's a one-shot game. There's no further afterwards. In the cooperative metaphor, there's a little bit of this thought that like we kind of reach this. I mean, we don't know how, but there's something with the stability concepts that say, oh, it has this feeling that we reached this as, we did this a lot, we did a lot of stuff, and eventually we got this like stable point where nobody benefits from sort of moving around this point. I don't think we have that same metaphor when we think about non-cooperative games. I guess I should pause here because you probably want to probably have a good response to me that to that. But I yeah. So what? And then I have a question about just incentive compatibility, which I know is we have some results about incomplete information matching and how it's kind of hard to find stable matching and like have the information necessary for reaching a match to be revealed. Somehow this doesn't show up here. I thought it, but I'm sort of curious why, or did I miss it? Yeah.
Can we, can I elaborate on the question, the last question?
So the last question is, I think, like Chakrabarti, I think Olszewski, and I shouldn't forget the third co-author, but there's a third co-author, like have this JET paper about the difficulty, let's say, of like if you have one-sided incomplete information, of getting matches that, once they reveal to you, you have a prior, once they reveal to everybody what they were, what the match is, can we keep this stable? And they have some results, some cases where you can get it to be stable, and in some cases that you can't. That there is no incentive compatible. So their definition of stability, which I admit I should know better compared to yours. Here you're sort of assuming we kind of reached the match and then that's it. We don't know, we don't know what information we had to reveal in order to reach the match. There they had to say there has to be some mediator who gets at least learns your type and in order to tell you what you're going to be matched with, right? Which is like the bare minimum if we think of there being some strategic interaction to reach to it.
So
I think your general question, Doron, is about what difference does it make to have the verifiability assumption or not in the spirit of Wilson? So in the first paper in the literature, in the Wilson paper that Qingmin mentioned, the issue was that the state is going to be exposed verifiable, and then there's no reason to impose incentive constraints. If that's not the case, which of course in many applications will be interested in studying, situations in which the state is not going to be exposed verifiable, then you have to impose the incentive compatibility constraints, and that actually complicates things quite a bit. I mean, there's a literature started by my colleague Rajiv Vora and many people following that shows, for example, that the Wilson core score that was in the Wilson framework non-empty in the domain of standard exchange economies doesn't satisfy that property anymore. So yeah, that and as I understood Qingmin's paper, you're not looking at the incentive compatibility question at all, at least so far, right?
No, yeah, but that's right. I do not look at that question at all, but I do want to address one of the questions that Ron raised. Okay, if I look at this kind of restrictions on players' belief, okay, so what is player N's belief? Okay, when there is no other player to deviate. Okay, so let's look at this. Okay, player N is the only player in this sighting. Okay, in this deviation, and Z prime is exactly equal to Z. Okay, which is basically that the player look at outcome Z. Okay, and what is this player's belief at Z, right? Because he's deviating from Z to Z, right? And if you look at this, okay, because player N is the only player, okay, so the convention of this is that this is a whole site, right? So therefore, player N's belief is actually just the prior belief conditional on observing his own type, of course, and that observing the outcome Z, knowing that outcome Z is generated by this quote-unquote equilibrium pi. Okay, and this is basically the rational expectations assumption, right? You know that the equilibrium mapping is pi. You observe outcome Z from this equilibrium, and what is your belief before you even consider deviation? Okay, that's going to be exactly this, right? So you update based on your observation of Z, right? So I think that answers your question. Where does the belief a player have conditional on even without considering the deviations?
Good.
Right. So
now I can explain my question a little bit better. So first, thanks. That was not a good way. Whatever theta prime n would have done in this matching, right? So I'm the same guy, same person, but different type. What if I tried to do what that other version of myself would have done? Maybe I would have been better off. That's not a thing you're sort of asking here, or you're just saying somebody made this matching happen, and at this match, your theta n type, your high type, got this thing, and your low type got this thing. The low type never had a chance of pretending to be a high type.
I do not understand that question, right? So suppose that you are a low type. Okay, let's call that low type theta n.
Sure.
And you try to say, okay, what if okay, so I try to mimic theta n prime, right? Well, if you are really low type, you're going to have some belief, right? That belief is specified by n. But your opponent do not know whether you are low type or high type, right?
Right.
And they are going to have their belief associated with this deviation. And they say that, hey, whether the low type or high type want to deviate, low type opponent or high type opponent want to deviate. If both want to deviate, okay, then they cannot rule out the guy being high or low. So therefore, they have to update their priors condition on both types. Then they have to 0 on the low type and probably 1 to the high type, right? I think that's captured here.
No, but this is all after we got matched, right? So this is you're looking at the world. We got matched. Now what?
Right.
I'm talking about that stage before we got matched. Before we got matched, I would have liked to get what I could have gotten if I was theta H rather than theta L, or the high type of myself rather than my low type. But I was never given a shot.
Well,
so suppose you're trying to implement this thing with a mediator who first, who like collects people's information, a la Meyerson, right? And then says, okay, here is the match that you guys are all going to be getting. And now, right? And then, right? So that's what I wanted to do. that kind of problem would have had an incentive constraint for the, for the low type to not report to be a high type and the high type not to be a low type,
Well,
right? Of the same person.
So
before.
Yeah. Okay. So Doron, what you said is just what I have here, plus one additional condition, which is that this pi function has to be incentive compatible. This one.
Right. That's what that's what I was saying.
But yeah, but as long as the belief updating is concerned, that's already captured.
Yeah, no,
right, by this restriction,
Right.
right? So basically, I could define stability plus incentive compatibility of pi, right? But the reason I do not want to do that is because of following, right? So a lot of times that the stability describes the limit of an adaptive adjustment process, right? It doesn't have to be the implementation through this mediator, right? We already know a lot of impossibility result even for the complete information problem, right? There is a conflict between incentive compatibility, but usually there is dominant strategy incentive compatibility and the notion of stability. Okay? But there we do not think that stability is a bad concept. There are adaptive process, adjustment process, right? That lead to that stability concept, right? Like the two papers by Crawford, right? Crawford, Kinor, and for example, that says, oh, there's an adjustment process to implement a stability.
So the one,
but of course, this adaptive process.
So the one that I know is like one that's like very myopic. Is that one the adaptive process you have in mind, where we?
Yes. Yeah.
Yes.
So there are different approaches. So Crawford Kinor is one of the ideas, but there's another idea by Rush that considers the random matching procedures, right? Yeah. So that's why I'm not willing to impose incentive compatibility directly on pi. Okay.
I have to think about it. I'm not sure I understand how that would work, given the fact that we know that if I, the incentive compatibility constraints are ones that for any game that I would run, right? Any game I can imagine running, they need to be satisfied if I'm somehow doing something that leads to this outcome.
But
I need to think.
Let me give you another. Let me give you another answer. This is something I have thought about. Okay, let's say that you introduce a dynamic game into the problem. Okay, so the two players are bargaining whether they want to go from Z to Z prime. Okay, so if you literally have a dynamic game, the weighting cost is going to be important, right? You know that there will be incentive compatible allocations, but with delay, right? And you can get some terminal matching outcome that can be efficient. But if you take into account delay, that's not going to be efficient, right? Well, if you want to consider a dynamic game approach, okay, how do you account for delay in a reduced form model? I will say that the stability concept captures what happens at the end. Oh, in the end, there are no further deviations. Okay, and what is the property of the quote unquote steady state matching situation? That's what I'm trying to capture here. But all the delays along the path has been ignored. Okay, but if you want to bring back incentive compatibility, I think it's reasonable to enlarge the outcome space. Not directly impose incentive compatibility on pi, but impose it on the enlarged outcome space, and then define a pi on that enlarged type space. That's number one. Number two is that if you want to consider, you want to consider something other than the myopic process, you really have to consider forward-looking incentives. And I think that corresponds to some notion of farsightedness better than the stability concept considered here. But I have to say that it's going to be very difficult to consider farsightedness. But I think even in complete information game, there are still unresolved questions over there.
Of course, I could keep going forever, Qingmin, but I think Roberto might have some smarter things to say than what I will.
Yeah, maybe Roberto, if you have any comments.
Yeah, sure. So I had put together a few thoughts. So there's a lot of good things about the paper. There's a lot of things to like about this paper. I think, one theme in economic theory in general in recent years has been the insistence on robustness. That is to try to obtain robust predictions to our theories. And I like to think of cooperative game theory as a way, another way to define robustness of predictions, in the sense that by being a more abstract approach, sometimes using axioms, not every time using axioms, but sometimes using axioms to order our thoughts and guide our, queries, help trying to make the predictions independent of the details of the interaction, the extensive form, whatever that is, I think is a good thing. That's not to say, of course, that cooperative game theory is assumption free. No theory is assumption free by definition. But it's certainly a more flexible approach in this sense, that it's assuming a fewer things. So I'd like to put this paper into the program, the general program that could be called Making Cooperative Theory More Useful. And certainly I wouldn't say that cooperative game theory has been useless. That's not a fair statement at all. I mean, there are very important results that have been derived from cooperative game theory, the connection with general equilibrium through, the equivalence or convergence theorems of the core, the value, and other cooperative concepts. The beautiful applications to the real world of all the matching theorems from, Gale Shapley, Shapley Scarf, etc., Roth and his collaborators. Those are all beautiful things, and they come from cooperative game theoretic work. But if you think about it, I think all these successful results can be characterized by looking at very large systems, would be understood as a competitive economy, and or simplifying assumptions are made so that we're looking at this ideal world where, in particular, there are no externalities, there's no incomplete information, etc. And the question now is, well, what happens if you want to make cooperative game theory applicable to systems in which, there's a finite number of agents? You're not going to take now limits of, n going to infinity. And you're going to allow, these new things that the standard approach, the classical approach to cooperative game theory ruled out, let's say coalitional externalities of different kinds or incomplete information. Then serious problems arise, and that's why I think the area is making progress, but it's making slow progress. I think one of the key difficulties in taking this step is that you can no longer use the characteristic function to describe the fundamentals of a game. And in the case of incomplete information, there's this complicated issue that, when a coalition of asymmetrically informed agents gets together, whatever they do, just in their conversations, some information is going to be transmitted somehow, and so it's very unclear at first to even define, okay, how are you going to define what the coalition wants to do? Because, again, as Qingmin pointed out in some of the examples, it's going to matter whether, all the types in the coalition are, for it, or just some types, and therefore you're going to be learning something about the types of the others in the coalition from the fact that they're putting the proposal on the table, etc. Right? So these are the difficulties that I think are fascinating and that we are trying to deal with. And I very much welcome approaches like Qingmin's that tries to be abstract enough so that you get away from the details of what interaction took place to lead to a given deviation or something like that, and just paying attention to the fundamentals in the problem, which in this case I agree has to do with these beliefs. Yes, so whatever we're going to be doing is going to be a function of the belief we came up with. So without paying too much attention to how that belief was formed, but now, you can certainly write down things as a function of, any such belief and come up with this reasonableness concept of beliefs and so on. So I think that's very powerful. That's where I see the power of the approach in this paper. A few quick questions were the following. I thought about I think three things. One is so Qingmin has at the end of the paper, when he connects with matching and networks, he connects under some conditions with efficiency. However, I suspect that's just those are nice results, of course, but I suspect that the general message here is going to be that there's not going to be an easy connection between a stability concept with incomplete information once incomplete information is modeled carefully, and efficiency, and that shouldn't come as a surprise, in the sense that even in general equilibrium, we know that with asymmetric information, we may have violations of the first welfare theorem. In game theory, of course, even with complete information, game theory being the science of externalities, we know that the equilibrium is not efficient, doesn't have to be at all. And I know that in my own work and other work in these areas, when we are exploring problems with either externalities, like Eric Maskin has been doing for a few years now, uh, um, uh, there are already difficult questions that tell you, look, even if you look at something like the core, the core may not be a subset of interim efficiency anymore. That is, you could have inefficiencies in the core. I know Edgeworth will probably be revolting in his grave if he's hearing this talk now. But or the Shapley value, that this is what Eric Maskin has been doing, and now we're generalizing what he did in work with him, where this solution that gives you the Shapley value without externalities, once you put externalities into place, actually some inefficient outcomes. So I think it would be interesting in Qingmin's paper to find out what is the scope of that. That is, how big the failure of this connection between the stability concept and efficiency is. Then the second question was, I think it would be very useful to connect your basic consistency, weak consistency, and strong consistency with these different objections that have been proposed in the literature, like the coarse objections a la Wilson, or credible objections a la Data Vora, or the sequential objections that I have in the paper with Kamishiro and Vora. I suspect there are very deep connections there, and it would be nice to understand them formally a little better. And my final comment ties to this last comment is you made a quick comment saying that randomness, if you consider random allocations, that wouldn't make a difference. I'm a little surprised to hear that, because Meyerson has this paper on the virtual utility core, to make the point that very differently from complete information, in complete information, it doesn't matter, even if you have transfers, a TU game, it doesn't matter whether the coalition is considering only deterministic objections or random objections, because any random objection can be subsumed into just a lottery over deterministic objections, and that's it. But with incomplete information, that's no longer true. It makes a difference. So in particular, this virtual utility core of Meyerson is actually a subset of the credible core of data and Vora, and so I suspect that if you introduce randomness here, there's going to be also a difference along those lines. But sorry, I took up probably too much time, but I can stop.
Thank you very much, Roberto. Maybe we should stop the recording now and then maybe talk a little bit